Very nice setup. Looks like a reunion from meetings of some 20 years ago in Torino, and I'm very glad to be here. Like most of you, I didn't know what to do when I got this invitation, and particularly that my good friends put me as the first speaker, so I even had less idea what to do. So I called Roberto a couple of weeks ago and asked him, what should I do? He said, oh, talk about something about models. That's the most I could get from him. So I tried to do my best. And also I should apologize for the slides. I prepared a Blackboard talk. And only last night I realized that there's no Blackboard here. So I put something together and hope it will be okay. I teach statistical mechanics at the Weizmann Institute. It's a graduate course, quite regularly. It's quite an extensive course. It's 28 hours, 28 classes of 1.5 hours each. So it's a quite extensive course for graduate students and advanced graduate students, and so in that context I try to put as much material as I could. But I also teach another course which is even more challenging. It's a course to physics teachers. Typically these are teachers, they have bachelor degree in physics, they've been teaching 10 or 15 years already in high schools, and then they come for kind of 2-year program to have a master degree in science education. And this I find a very difficult task, explaining statistical physics to people who are, mathematically not that well-oriented mathematically, and they've been in classes for a long time ago, and to teach them something relevant, something that they can maybe talk about in class in high schools. I find it very difficult, and I've been teaching it for several years already, and I still don't have the right scheme how to do it. And I would be very glad to discuss this kind of issues during these meetings. Okay. So following the advice of Roberto 2 weeks ago, he said, oh, why don't you talk about soluble models and how you use them in classes of statistical physics. Okay, so that's what I did. And what I decided to do is to talk about symmetry breaking and long-range order in low dimensions as a broad scheme, and then talk about various aspects of it in equilibrium and out of equilibrium, and see how specific models can enter there in explaining the issues that come up in this thing. Now this is quite a broad topic. I typically in class I use maybe 2 classes of 1.5 hour each in exposing this thing, but not in one piece. I mean, this is done scattered during the course, various aspects of it, the equilibrium, the non-equilibrium, and but I would say overall 2 classes for what I'm going to talk about. Okay, so the first thing is to start with the famous Landau-Pyers argument. You say, okay, you have one-dimensional system, equilibrium, short-range interaction, finite temperature, no long-range order, right? That's and the argument is very simple. You say, one says you have this system, one-dimensional system composed of pluses, minuses, Ising, like you have a typical configuration like that. You have n is basically number of density, the number of contact points you have there, and each contact point between the plus and minus costs you some energy, so that's the energy, E times n, the energy of the particle, and then there is the entropy, which is n log n minus n. And clearly the Landau argument says that at any finite temperature, if you look at this term, the entropy is going to win over the energy, and because of this n of n. And in fact, you minimize it, and you find that n is finite at any finite temperature. And therefore, you cannot have a full string of all of them of the same type, either all plus or all minus, and therefore you cannot break the symmetry of plus and minus. Okay, that's the usual Landau argument. Now you can look at it also dynamically, and you say, okay, suppose you start with a system with all pluses, you create a droplet of minus by some fluctuation, and now you look at this and you see how it devolved in time. And you say, okay, you have this droplet, and basically it doesn't cost for this boundary to diffuse around, right? Because it's, when I flip this plus, it's at the boundary, it can just grow or shrink without any energy cost. And therefore, once you create a droplet, it will just take over, and you cannot maintain the long-range order where the system is predominantly up. It will just get mixed and everything. So that's the usual argument. So it's interesting to explore where the basic assumptions of this goes wrong. And clearly here you use the fact that it's a short-range interaction, right? Because you say that the energy per kink here is just n, they don't interact. Kinks far away don't interact, it's a local interaction. Clearly, if you take a long-range interaction, this is not going to happen. This is not going to take place. And we want to see how this is going to be violated. The simplest way is to consider a model that like Dyson and many other people in the 60s take interaction, Ising model with interaction that decays like some power law of the distance. Okay, so that's long-range interaction. Now, and you want to ask what happens as a function of alpha, of this exponent alpha, can you maintain long-range order or not, depending on this power. And the very simple way to explore it is just to look at the system, make a droplet of length little l in a system, very large system, very long system of length capital L, and you ask, what's the energy cost of this droplet, right? If you have short-range interaction, the cost is just 1 or 2, it's just a boundary. But here, that's not the case. And if you just look at it, the energy cost turns out to be of the following form. It's little l times capital L to the power 1 minus alpha. You just integrate the interactions. And then there is L to the power 2 minus alpha minus 1 with some coefficients. Okay, so basically, that's the energy of making a droplet. Now, then you see the following. Depending on alpha, then the energy cost is the following. If alpha is larger than 2, then this is capital L to the power 1 minus alpha. This goes to 0, because it depends on L is the length of the system. This goes to 0 if alpha is larger than 2. If alpha is larger than 2, this goes to 0. And then therefore the energy cost of making a droplet is just independent of the length of the droplet. And this is like short-range interaction, because you make a droplet, you flip it, the energy cost does not depend on the length of the droplet, and this is like short-range interaction. And so that's for alpha larger than 2. What happens if alpha is between 2 and 1? For alpha between 2 and 1, you see here L to the power 1 minus alpha, this is power negative, and therefore this goes to 0, it doesn't cost anything. But there is a cost here, which is a positive power of the length of the droplet. And therefore, to make a droplet, you pay energy which is proportional to some power of the length of the droplet, and therefore the droplet tends to shrink. And that's how long-range order can be maintained, because when the droplet, there is a force on the droplet to shrink, and therefore at sufficiently low temperature you raise a droplet, but it shrinks, and eventually if the temperature is low enough, you create these droplets at a very low rate, and before creating a new droplet, this one just shrinks to 0, and therefore you can maintain long-range order. Okay? So that's alpha between 1 and 2. And what happens if alpha is less than 2? If alpha is less than 1, it's even more severe, because then the energy of a droplet of length little l costs like a power law of the length of the whole system. It costs a lot. In that case, the energy of this model is not extensive. That is, the energy does not scale like the length of the system. It scales like the power L to the power 2 minus alpha, and if alpha is less than 1, this is L to some power larger than 1, and therefore then that's really long range interactions, and you have to do something else. Okay, so that's the simple argument how you go out of this. Okay, you can use this model. It's a very interesting model. You can use it to explore many other things. For example, you can look at the critical behavior of the model when you have a phase transition. It turns out that if alpha is between 1 and 3 halves, it's a mean field kind of transition. If alpha is between 3 halves and 2, it's not mean field, and this is basically done numerically. People don't know what to do. Alpha equals 2 is a very special case. That's again an opportunity to introduce another subject, because alpha is equal to 2 is a special case of a mixed order phase transition. That is, it's a phase transition which has a mixture of properties of first order and second order phase transition. That is, it has a diverging correlation length, right? But the magnetization, there is a discontinuity of the magnetization. So it's a kind of first order phase transition. There is a phase transition point. It's a first order in a sense that there is a discontinuity of the magnetization, but there is an infinite correlation length. So it's very special. It's related to Kosterlitz-Thouless phase transitions, so you can take this model and go to, if you want to talk about Kosterlitz-Thouless, and although it's a one-dimensional model, you can represent it as basically charges which interact logarithmically. And, okay. So that's an interesting model. So this is a very simple argument to show that when there is a long-range order, when there is no long-range order in one dimension, depending on the interaction length. But if you want to make it concrete, or you want to make an exact statement, you have to go to Koval-Frobenius theorem, right? Which basically takes the transfer matrix of this system, and you ask, does it look at the largest eigenvalue, and see that from the theorem you can show that as long as the transfer matrix is finite, you don't have a phase transition. The largest eigenvalue is unique, and it says the following. So the theorem says the following. Suppose you have an n by n matrix, finite matrix, where all matrix elements are positive. So this is kind of property of transfer matrix. Then lambda is its largest eigenvalue. You say that first lambda is positive. Then the corresponding eigenvector has all positive entries, and lambda is non-degenerate, right? That's the theorem. Now it's very to prove it in class, and that's a problematic. It's rather lengthy, but there is very simple proof for symmetric matrices. And I usually tend to show it. It takes a few lines to show that this is correct. And so in this setting, basically what happens is that what you can show that there is no phase transitions in one dimension as long as this the transfer matrix is finite, and the largest eigenvalue is unique. There is no degeneracy, and therefore it's analytic in the parameters that define the model. Okay, that's the issue. Now the proof for the symmetric case is very simple. So let me just outline it. It can take 20 minutes in class, and I think it's very interesting. First of all, the largest eigenvalue has to be positive. Why? Because the trace of A is a matrix of positive elements. The trace of A is sum over all the eigenvalues, which is positive, and therefore the largest eigenvalue has to be positive, right? Okay, so that's very simple. Then you want to show that the components of the eigenvector are all positive, because they should correspond to the distribution function that correspond to this eigenvalue, right? That's the probabilities of having the system in state 1, 2, 3, and they have to be positive. So all these have to be positive. To show that, one can show it in the following way. This is the it's an eigenvalue of the problem where the u's are the eigenvector and it's normalized. Okay? Then clearly, I just multiply by ui and sum, then lambda, which is larger than 0, we know it's positive, is just equal to this, right? And it's absolute value because it's positive, so it doesn't matter. But then this is less than or equal to when you put absolute value here. Xi is absolute value of ui. So clearly this lambda is less than that, right? Okay, that's very simple. On the other hand, if xi is just a normalized vector, sum over xi squared is 1, then clearly the quadratic form of this, because aij is also positive, then this has to be smaller than the largest eigenvalue, right? Because that's the most you can get with the quadratic form, the largest eigenvalue. And therefore, it has to be equal. If it's less than lambda, or smaller than lambda, or larger than lambda, it's clearly sum over aij xi xj is equal to lambda. And lambda is the largest eigenvalue, and therefore it has to be equal, lambda has to be, or the xi's have to be an eigenvector in order to satisfy this equation. And therefore the xi's are basically eigenvectors, the eigenvectors that correspond to lambda. So the xi is positive entries, it's the absolute value of the ui. So if you have a vector ui, which is an eigenvector with the largest eigenvalue, and then if you take the absolute value of the components, they're also eigenvectors. So it's positive, all of them are positive. Okay? And then you can show that it has to be that. And so you have all entries are positive. And of course, if one of them is 0, if suppose x1 is 0, then because all aij are positive, then all the x's have to be 0, right? Because the aij are positive. Therefore, all the entries are positive. All the entries in this sector are positive. Okay? So that's basically the proof. And then non-degeneracy, you have to show that it's non-degenerate, otherwise the whole thing doesn't work. So suppose you have two vectors, ui and vi, and they are eigenvectors of that largest eigenvalue. Then, since the entries, all entries of the u's and the v's are all positives, as we showed there, then the sum of ui and vi has to be is positive. But they have to be orthogonal. If you have two of them, you can always choose them to be orthonormal, and therefore it can't be that you can choose two orthonormal eigenvectors that satisfy that, and therefore this unique eigenvector. So that's it. So it's something one can show in 20 minutes in class, half an hour, while going through the whole theorem, and for general non-symmetric it's much more complicated. Okay, so that's, I think, very useful.
David, and where you use explicitly symmetry?
Sorry?
Where have you used explicitly the symmetry?
That you have, that that if you can diagonalize it, and it's orthonormal, and it's real, and that's where it's used. Okay. Now, one interesting thing is to explore the limits of this kind of theorems. So you use the fact that it's a finite matrix, right? That's very important. What happens when the matrix is infinite? And to explore that, and then of course the theorem doesn't work, and there could be a phase transition when the transfer matrix is infinite. And for that, there is a very simple model. That's one example I would like to discuss, is to show that when the transfer matrix becomes infinite, you can have a phase transition and everything is good. And the model, the simplest model I can think of is that of depending transition. Okay? The problem is the following. You have a substrate, and there is an interface. It's a one-dimensional interface, and it's just fluctuating above it. And there is a short-range interaction between this interface, between this line and the substrate. Okay, that's the problem. And you asked, it fluctuates because it's a string, and it's attracted to the substrate. Now, clearly, at low temperatures, very low temperature, fluctuations are small, and the interface is going to be more or less glued to the substrate, right? It's going to fluctuate, very small fluctuations above the substrate. Now you turn on temperature, you heat it up, and at some point, this interface is going to take off. It's going to deping, okay? So there is a pinning transition in this one-dimensional model, okay? It's a one-dimensional. And that's a clear demonstration of, where you can explore this Perron-Frobenius theorem in the case where the transfer matrix is infinite. Okay, so the way to do it is the following. To model this problem, let's look at a restricted SOS model. Okay, so basically you have, this is the interface, its heights. The heights are integers, and this on a lattice. Okay, that's very simple. And it's solid on solid. So hi, the height at size I is integer, and it's restricted solids on solids in the sense that hi plus 1 minus hi, the difference in height between two adjacent sides, could be either 0, plus 1, or minus 1. Okay, so that's a typical configuration of the interface. And then you have to put interaction with the substrate, and the interaction is whenever h is 0, that is when it's at the interface, there is some energy gain. Okay, it's a minus v times that. So basically, this is the Hamiltonian. And it doesn't cost to make any energy to make a kink, so that doesn't enter into the Hamiltonian, but that's the phase space. That is, hi's are just. So basically, that's the Hamiltonian. This is it. And you want to try to look for the pinning transition. Okay, that's the issue. Okay, so here is the transfer matrix. The transfer matrix is just, if you are far from the interface here, then hi could either go to hi minus 1 or to hi plus 1, because with just probability 1, and 0 elsewhere. While if you are close to the interface, where we are here, hi is equal to 0 or 1, there is an energy cost that's e to the 2 beta v. V is the interaction with the substrate, and e to the beta v here and there, and basically that's the transfer matrix. Symmetric form, okay, but it's infinite. If you look at this transfer matrix, you see that, let's look at the largest eigenvalue of this matrix. Clearly, if you take some height h, which is not close to the origin, the equation is that. So basically, it just, del squared psi is just equal to something times psi. And it's just like if you want, like a free quantum mechanical particle, which is moving there. On the other hand, if you are at the origin, there is an energy which is e to the 2 beta v. So basically, it's as if there is a quantum mechanical particle moving in a flat potential with only potential at the origin of strength, which is e to the 2 beta v minus 1. Basically, that's the story. So you have a quantum mechanical particle moving in a potential like that. It is an infinite barrier at origin, that's a substrate. There is the energy that's coming from the interaction with the substrate, otherwise it's free. Okay? Now, it turns out that if you look at this problem, if this well is deep enough, that is, if the potential is high or the temperature is low, this well is sufficiently deep, you can have a ground state here which is localized. There is a ground state which is localized within this well. Okay? So basically, you can have a ground state which is e to the minus kappa h. It decays exponentially with h. It's not a propagating wave. It's not e to the ikh, but it's e to the minus kappa h. And if you want to look at the what's the probability of finding this interface at height h, it just HTT is the transfer matrix to the power n, just this matrix element of the transfer matrix. And basically it is psi h squared divided by psi psi. So that's it's basically the matrix element of h in the ground state. Now, if you have a solution like that, then clearly the probability of finding the interface at height h is just e to the minus 2 kappa h, and it's exponentially decaying, means that it's bounded to the substrate. Okay? So the question is, what happens as the potential grows, become shallower and shallower? At some point, this k goes to 0. And what happens is that the bound state here is going to go up. At some point, it's going to reach the top, and it's going to join a band of states that are the free states that happen there, and you get a phase transition. So that's how the phase transition takes place. And if you want to locate it, you can solve the equations at the boundary. It's very simple. When kappa is equal to 0, and you find that the critical value of the potential is e to the 2 beta v is just 3/2, you get a phase transition. So that comes because you have an infinite transfer matrix. That is, H could go to infinity. It can go to infinity. What happens if you put an upper ceiling on the interface? Suppose this is the substrate, this is the interface, but H is just bounded from above. It cannot go too far. In that case, of course, the Perron-Frobenius theorem applies, and there is no phase transition. And in fact, in that case, it's like you have a particle moving in a potential like that, where H is restricted to move in a finite domain. And therefore, there is always a bound state in that case, and the interface never gets free. Okay, so I think that is a very nice exercise to demonstrate various aspects of this theorem, where you can have a phase transition, where you don't, etc. Typically, a question that comes up when you teach that is, when you look at this transfer matrix, there is a lot of 0 elements in it, but yet you apply the Perron-Frobenius theorem, right? It's okay. And the reason you can do it, that has to do with ergodicity, because if you take sufficiently high powers of the transfer matrix, basically all these are going to be filled up with positive numbers and everything is okay. So the interface, you start at some site, you can go to any other height if you do that. So you take just the power of the transfer matrix and you're okay.
A prophet of my position as a chairman. Essentially, you are mentioning the last slide that showed us ergodicity, and you just explained to us what you meant with it.
Right.
Do you find that this, to my experience, this concept is very hard to be catch by the students?
Right.
Because it is presented in very many different ways.
Right. Right.
And they don't really find how to bridge different ways to discuss
Yeah.
that.
Yeah.
You may say,
in that context, it's very simple. It's trivial. I start at height h, and I go sufficiently far. Then if I just go to the next side, the h could be either +1 or -1, right? Because that's a restricted SOS. But if I go sufficiently far, I can reach any height that I want, and in that sense, it is ergodic. You can reach whatever h. Getting into ergodicity, that's a different ball game. Certainly not within this model. You have to.
No, but just to point out that every time this concept pops up frequently, many kind of explanation of models. And I want just to point out that this may be difficult for the student to realize what hell of ergodicity you're speaking here, with respect to the one we heard about from Boltzmann, and the one they heard about from another.
Yeah, but that's a good opportunity to try to make
the
And as you will see in the next model, there is going to be another touching point. How are you doing with time? Okay. Okay. So this is for equilibrium one-dimensional systems. How about non-equilibrium one-dimensional steady state? In that case, of course, there is no theorem. There is nothing. Landau argument doesn't hold. The one for Bennet doesn't hold. And in principle, you could have phase transitions in 1D in non-equilibrium steady states. Okay. So, and it's interesting to demonstrate that in some models. There are many setups you can do it. I choose to do it with two models that I like. One is the bridge model, and the other one is the ABC model. So let's see, I just discuss with one of them or both or whatever. So how to get a phase transition in one dimension in non-equilibrium steady state? That's the issue. Okay? Okay, what is the bridge model? So this is good usually in a context of simple models, and this is one of the simplest I can think of. Now the bridge model is basically tacit, the asymmetric, totally asymmetric exclusion process, and it's the following. So you have a lattice, and on each lattice point you either have a plus particle or a minus particle or a vacancy. Okay? Plus particles move to the right. Okay? Minus particles move to the left, and vacancies are vacancies. Okay? So the moves are the following. If you take a pair of nearest neighbor sides, and it's plus 0, the plus moves ahead, and then it goes to 0 plus with weight 1. So it just moves. If you have 0 minus, it goes to minus 0 because minus goes to the plus goes to the right, minus goes to the left. Also with weight 1. Now what happens when they come head-on, the plus and minus? They come, two particles, they exchange. Typically you can take it with weight q, they exchange. But for simplicity, let's say q equals 1 to make it very simple. Okay? So basically, for the classes, this is just a tacit, right? Because each time it encounters either a plus or a minus ahead of it, it just jumps. So it jumps to the right. While the minuses jump to the left, and these are two tacits, okay? The interaction between them comes from the boundary. So the boundary terms are the following. You either, okay, what happens at the boundary? At the boundary site 1, if there is a vacancy, here, you introduce a plus particle on that side. If there is a minus, the minus goes out with some rate and leave a vacancy. Okay? Similarly on the other side, if a plus particle comes here, it goes out with some rate, and when there is a vacancy here, a minus comes in with some other rate. Okay? So basically that's the model. You introduce pluses with weight alpha plus here, you take them out with weight by beta plus, and you introduce minuses from that side with alpha minus, take them out with beta minus. That's the model. Okay? Now, okay, here is the model. It's very simple. You can think about it just while it's the simplest case is to take where alpha plus is equal to alpha minus, beta plus equals beta minus. That is, it's fully symmetric. That is, you introduce the pluses with the same rate that you introduce the minuses, and you take them out with the same rate, and therefore you have a left-right symmetry in the problem. And the question is, what happens to that symmetry when you look at the steady state? Okay. So clearly, if this alpha is small, these alphas are small, alpha plus and alpha minus are equal, you introduce particles at a very low rate, while the betas are large, you take them out very fast. Then clearly there's going to be very low density in this bridge. Okay, it's kind of a bridge that cars coming from both sides and they just take over. And so if alphas are small and betas are large, clearly few cars are coming, they leave very fast, and therefore the bridge is sparse. There are sparse particles there, cars, and therefore it's going to be symmetric, right? There's no question that the number of pluses and number of minuses in the bridge are the same. On the other hand, if you take the other limit, that is large alpha and small beta, that is, you introduce a lot of cars, but you hardly take them out, then clearly you can have symmetry breaking. That is, that one of the species, they say the pluses, take over, it fills the bridge, and then there's no room for the minuses to enter, and it can break the symmetry. And therefore you can have, in principle, you can have a phase transition which breaks the symmetry in that limit. Okay? Here is some numerical run of the dynamics of the bridge. What is plotted here is J is the current of the pluses, and J plus is the current of the pluses, and J minus is current of the minuses. I could have plotted the density of the number of pluses or minus number of minuses is the same. So what you see that it's a two-state situation. Either it's predominantly pluses, and it stays there for a while, but at some point there are few cars coming from the plus side, particles leave, and there is a chance for the other side to enter. It's like what you experience in a narrow bridge, right? Cars are not coming from one side, there is a chance for the other to take over, and then there is predominantly minus. So basically that's the bridge. And of course, if you average it, you get zero, right? Everything is zero. So where is the phase transition and how you can see it? The way phase transition shows up, and this is again ergodicity, Roberto, is what happens to the flipping time, okay? When this bridge becomes larger and larger and larger, right? If this flipping time becomes long or increases with the system size, increases sufficiently fast with the system size, in fact what you see is that once the bridge is full basically with pluses, the flipping will, in the thermodynamic limit, when the bridge size goes to infinity, will just stay there and it will never flip, and that would be asymmetry breaking. And that's basically breaking of ergodicity. The way we talk about it, we talk about phase transitions, that of course you can have this state and that state, but the probability of going there goes to zero and you break ergodicity. Okay? So the issue is to explore what is the flipping time between these things, the average flipping time. Okay? So that's the bridge model. And the way to do it, it's a very nice, again, a statistical mechanical problem. Looking at it in a limit of very small beta. Beta is the exit rate from the bridge. Okay? Suppose beta goes to zero. That is, when a particle enters, it just moves very fast to whatever it's going to move, but eventually it cannot exit, or it exits in a very low rate. Okay? So in that case, a typical configuration is the following. If you introduce a plus particles from this side, right, it will just go over, and then it gets stuck on the other side, on the right-hand side, because beta is small, it doesn't go out, it goes out very rarely, and you get all the pluses basically accumulating on that side, all the minuses accumulating on the other side, and if there are zeros, they will be in between, in the other axis. So this is a typical configuration in that limit of beta very small. Now, okay, but beta small, but it's not zero. So every now and then something happens. What can happen? What can happen is, for example, that this minus goes out, and there is a vacancy. And if this vacancy is here, it could start propagating and join this vacancies here. Or, okay, that's one possibility. The other possibility is that there is a vacancy here, but then quickly plus enters here. And the plus will go and will join that. Okay, these are the two possibilities. And similarly, in here. Okay? So if you look at this configuration, what is the dynamics of that configuration? The dynamics is the following. this is x. X is the length of this minus domain, and y is the length of the plus domain. And of course, x plus y is less than n, less than or equal to n. N is the length of the system. Then what could happen? What could happen is that this xy goes to x minus 1 y. That is, just a 0 enters here and it joins here, and y, basically x goes to x minus 1 and y stays intact. Okay? And this happens with some rate a. Or when this minus goes out, a plus enters, and what happens is that x goes to x minus 1, but y will go to y plus 1, because the plus is going to join here. So you can have this move with rate b. So either x goes to x minus 1 and y stays the same, or x minus 1 plus y plus 1 with rate b. And similarly from the other side, and a and b are just 1 over 1 plus alpha, or alpha over 1 plus alpha. Basically, these are the rates. Okay? So now you have the following problem to explore. You have this xy plane. X plus y is less than n. So that's the line x plus y is equal to n. And you have the system here, means that x is x and y is y, and that refers to this configuration. And the moves are the following. With weight a, you know, x goes to x minus 1, or y goes to y minus 1. And with weight b, x goes to x minus 1, but y goes to y plus 1, or vice versa. Okay? So basically, these are the moves of this point. And okay, so the issue is to do the following. If you want to explore this flipping time, you start with a state where all the system is plus. Okay? All the system is plus, you start here, right? And then you start diffusing with these ways, so it just starts moving. But there is a bias for it to move to the left, right? Because it moves in that direction, basically, it moves here. So eventually it gets stuck, it gets to the axis here. What does it mean that it gets to the axis? X is equal to 0. X equal to 0 means that you have pluses here and zeros all the way. Once you have zeros all the way, then very quickly with weight alpha, pluses are going to fill the system, because here it's blocked, here it's beta, and it cannot move. And you reach back the state where y is equal to n, right? Because alpha is large, there is no blockage. Here, particles cannot enter, the pluses cannot enter because of the minus, and it has to wait for the minus to leave, and that rate beta is small. But when there is no minuses here, it's all zeros, then very quickly the pluses enter and fill it in. Okay, so the story is the following. You start here to make a diffusion, you get stuck, you get back to the origin, and you go back. And you do that, a lot of loops. Basically, so what you have is a lot of pluses, it's basically filled with pluses. Every now and then there is a little minuses entering, but then they go out and whatever. Until there is some move, there's some probability for it to go all the way and get to that boundary. Basically, it's a first passage time. When it gets to that boundary, it means that basically the x's are depleted, and then all the minuses are going to enter into the system, and there is a flipping. So once it reaches here, it will just eventually here, and it starts the same process doing it here. Basically, that's the dynamical process that we are talking about. So the issue is to calculate, to find what is the first passage time to start from here and to reach this boundary without ever hitting that boundary. And that would give the flipping time. And it's clearly the flipping time has to be exponential because there is a bias to move in that direction. And you can do the calculation. That's a more. But it turns out that the tau goes like n to the power 3/2 times e to some kappa n, So it's exponential, but there is a prefactor which is n to the power 3 halves, because it's the first passage, and kappa could be calculated, and everything is okay. So the flipping time is exponentially large in the system size, and that's how phase transition or symmetry breaking sets in this model. Okay? And again, there is ergodicity breaking because the probability of exploring the other part of phase space goes to 0 in the thermodynamic limit that n goes to infinity. Okay, there's one issue, another interesting issue. How much time do I have? 10 minutes? 10 minutes. And this is the following, which again can be demonstrated in this very simple model. And that's stability of the wrong phase in an ordering field. What's the issue? The issue is the following. Typically in equilibrium, when you look at the phase diagram, this is HP phase diagram, say any magnetic system. You have a phase transition at some critical point. You have a coexistence line here. And when the ordering field is positive, you have positive magnetization. When the ordering field is negative, you have negative magnetization. You cannot have negative magnetization with a positive field as a stable state. Okay, eventually it could be metastable, it could be whatever, but it's non-stable. The stable phases are these. Okay. Now, in non-equilibrium setting, if you have non-equilibrium steady state, it could happen that the analogous HT phase diagram is such that both phases are stable in a region around H equal to 0. Namely, that for H positive, you still have a stable negative magnetization phase, analogous of that, and vice versa for the negative phase. So that's possible. That's basically a violation of the Gibbs phase rule or whatever, which we know is satisfied in equilibrium. In non-equilibrium, this is not the case. And this model, this bridge model that I discussed, can serve as a very simple demonstration of how this can happen, how this could happen in a very simple way. And the way to do it is to consider the following thing. Suppose you started with alphas, both sides, and betas on the same side, and they are all the same. Now, what is the symmetry breaking field? I want to break the symmetry between the pluses and the minuses, and therefore I will consider the beta plus and beta minus to be different. Suppose beta plus minus is beta times 1 plus minus plus h. Okay. So the exit rate of the pluses is different from the exit rate of the minuses on the other side, and this would be a symmetry breaking field. Okay. Now you can go throughout again in the limit of beta small. Again with this kind of setting, the probabilities of this diffusing particle in this plane is the following. Now it's not A, but here it's A times 1 plus H, and B times 1 plus H moving in that direction, while here it's A1 minus H and B1 minus H moving in that direction. Okay? So you break the symmetry between plus and minus, so it's not 45 degrees as it's moving, there is some tilt. Okay? But for any small, if the field is sufficiently small, what you see is that this phase and that phase are all both stable. This phase is where it's basically all pluses. This phase is where it's all minuses, because the bias is in that direction. So eventually there is a net bias when I'm here to move in that direction, and there is a net bias to move in that direction. So both phases are stable. But it's true that this is a little bit more stable in a sense that the flipping time from the plus to minus is a little bit different from the flipping time from minus to plus. But both grow exponentially in the system size. and therefore they are both stable. When do you get, what is the critical field? This is for small field. What happens at high field? At high field is when the probability going down here, which is A times 1 minus H plus B 1 minus H, is equal to the probability of going up there, then you no more have a bias to move down. Okay? And that's the critical field. And you do that when A plus B is this. So basically when H is smaller than something, you still have the bias and both phases are fully stable and like that. Okay? So basically that's what I wanted to say about this model. They enter to 5 minutes or?
Yes, I would like to leave some space for.
So we can stop here and we can make discussion. Yeah. Otherwise, I can discuss.
If I have questions, because there are.
Okay.
Okay. Is there anybody who would like to introduce discussion, make comments, or?
I just want to make a remark that you know, this thing, when you show it in a course, it's there are other models you can talk about. It's really scattered throughout the course. It's not something that you in one piece you bring together. You start talking about something, and then the equilibrium, and then the L1 forbidden, and then you take a model sometimes where you violate it, and then okay. And when you get to non-equilibrium, that's later in the course. You start talking about this and remind. So it's, I would say, net 2 classes of this kind of subject.
Just one thing that occurred to me when I heard your talk is that maybe, especially to achieve what Roberto said, to sort of open our field towards interdisciplinary applications. Of course, the notion of thermal equilibrium is something that in most interdisciplinary applications doesn't appear, right? So thermal equilibrium is something very special. Now, you begin by characterizing phase transitions as singularities in thermodynamic quantities.
Right.
But this is a notion, as you explained, that doesn't apply to non-equilibrium phase transitions. So I wonder if one shouldn't maybe introduce the concept of phase transitions much earlier as a from a kinetic point of view, and say phase transition means that switching times between macroscopic states become exponentially large. That kind of definition. Of course, it's sort of more complicated to introduce in the beginning, but it's much broader, right?
You're absolutely right. And in fact, I do it when I talk about these droplets and the time. But the question is what order you introduce things, and so it depends on the course. I mean, how you do it. But of course, I think that's basically the core of these issues. And one should introduce them in this way.
At least at an early stage, to see that one can view all these things in a kind of dynamical
way. Absolutely. That's why these notions of droplets and their behavior is very, very interesting.
So finally, what is the answer that you give to the question in your title? What is the role of models in teaching statistical physics?
I think, what is the role? Theorems are theorems. If you want to understand them, and if you want to understand basically when they do not apply, then getting to models, explicit models, and demonstrate the limits of validity of things is very important. That's how one can understand basically the meaning of a theorem. Why. And that's why devising all these simple models to demonstrate some points is very important. For example, this issue of having a wrong phase, a stable wrong phase in one. This is a very general thing in non-equilibrium, and there are many models. The two model, and there are other models. That one can see that you can have a wrong phase, although you put a field that tries to drive it in a different phase. And taking a very simple model and seeing how this can come about, I think it serves some purpose.
But from let's say, from my point of view, if I think, for example, to the first model spoken about, the easing in one dimension with a ferromagnetic coupling which decays as a power law.
Okay.
I think that this model might be used to introduce and discuss several different concepts, because they have the case that critical temperature is zero, when the critical temperature is different from zero.
Sure.
You have first and second order phase transition.
Absolutely.
You have even the non-additive case.
Absolutely.
So, I mean,
you can branch to
yes,
whatever you want.
From this point of view, I think that really the one-dimensional easing model with this type of ferromagnetic.
Right.
I mean, it's special. I mean, it allows much more than other typical.
Absolutely.
Typical model.
Absolutely.
The bridge model is perhaps the simplest case of non-equilibrium symmetry breaking, perhaps. And you can also discuss about anisotropic random walk, phase passage problems. So perhaps another, answer to the question of the role of models is, if you choose good models, you can use one single model to introduce and discuss several.
Absolutely. And this was the point of presenting all these models like that. That you can branch, you can even get to Costa-Listaulis if you want from this 1 over, R to the alpha model. You can branch to many, whatever. It depends on the order of the course. You cannot talk about Costa-Listaulis right at the beginning of the course, right? You have to introduce concepts of phase transitions and this and that. And maybe you can come back to it later in a course. If you have this model in mind and you looked at it from a different one perspective, you can look at it from a different perspective later on when you talk about different things. So, and basically that's how I use it in a course. I use several models, and whenever a concept comes up, I try to demonstrate it or explore its validity in some of these models. And there are plenty, the choice of models is really arbitrary. One can choose whatever model you want, because these kind of things show up.
There could be some of them, but I think Paolo was some of these models that Paolo was suggesting are probably more appropriate to provide they contain a great deal of information that can be.
That's why I choose these ones, because they really allow you to branch to many other things. First passage, random walks, all kinds of.
Other questions?
No, to came back to the first comment. I sometimes wonder, often the way non-equilibrium is presented is basically, I arrived 15 minutes later, but it's basically violation of equilibrium theorems or exception to equilibrium theorems, in a sense. And so I'm coming back, it would be also possible maybe to have the opposite view. Traditionally, logically, we first teach students equilibrium.
Sorry, what is the equilibrium theorem?
Sorry?
What is the equilibrium theorem?
Equilibrium theorems, theorems which work in equilibrium and in equilibrium statistical physics. Mermin-Wagner theorem, for instance.
So, a big class of...
Yeah, theorems, plural. There is a huge class of results. And then we basically teach students that there are systems which are non-equilibrium. Do you think that it could ever be possible to first teach non-equilibrium things? I don't know. It could be
I never tried it.
No, I wonder.
You mean that you could decide to explain equilibrium starting from
non-equilibrium as a special case?
Of course, it's not done this way.
Well, essentially, it's part of what was.
It was exactly what
you start from a kinetic approach, and then from this kinetic approach, you bring. Because I would say that the attitude of people teaching statistical mechanics from the point of view of equilibrium is a sort of, let me say, for some cultural tradition, at least in Italy and no elsewhere, is a sort of theoretical approach. While the non-equilibrium forces you in some sense to introduce dynamics, and dynamics is, at least from the point of view of some of us, a more general approach. but that will be discussed for a long time. I have another comment. I think that one very important thing is very hard to teach to the students is the importance of finite attitudes that appear everywhere here. And the fact, and the very idea of thermodynamic limit is a concept that takes a long time to enter a student mind, because apparently everything is sort of simplification, while it's a very subtle point. Yeah. It's a very, very extremely subtle point. Yeah. Another comment I had while hearing your examples, that's perfect obviously for classes for physicists, but if you try to explain to some people coming from the outside, and very problem in my opinion is not these basic concepts that we consider important in statistical physics. In many cases there is a lack of knowledge about the basic mathematics. Anything which concerns matrix theory is almost unknown to many people. That's a very great problem. I think that teaching this kind of matter without this background is practically impossible.
This is useless for non-physicists. I think it's there's no point in trying to explain things in this way. And basically, I would like to have some advice on how to teach statistical mechanics to teachers. I still haven't cracked it, how to do it. For example, I would like to reach, when you teach teachers, high school teachers, I would like to reach the point where I explain, things that they can see, daily life, like what is temperature of the universe, black body radiation, what is, all kind of temperature of sun, so you need ideal gases, you need quantum mechanics, you need, how do you explain it, and then do you need, okay, if you don't want to do it, then you have to do ensembles first, right? How do you do thermodynamics of ideal gases?
In your opinion, transition, we are exploiting an analogy with the quantum mechanics, which is familiar to physicists, but in general,
no, this is
all the other
I would like to teach, ideal gases and ideal quantum mechanical gases to non-physicists. How do you do that? I really don't know how to do it.
Your students have a bachelor in physics, right?
They have bachelor in physics, but it's about 10 years old, 10, 15 years old. So it's something in the far past. They have never used it in classes when they teach, and so that's a very difficult problem. It has nothing to do with this talk.
Okay. My question is, when you want to teach the non-equilibrium, what is the kind of general result which they would get from such a course? Or what would we like to grasp them? They're nice models, and each model looks a little bit particular, and you can explain things. But in contrast to equilibrium, what was called equilibrium theorems, what is the what are the 3 or 4 principles of non-equilibrium we want those teachers to grasp?
That the steady states are more complex than what we are used to. Okay, e to the minus beta h, okay, we know, that's fine. The phase space is much larger, and these are examples. I don't know how to make a general statement about what are non-equilibrium steady states.
That's why it's hard. I mean, what is the universal? Is there universality, right? And if there is no universality, it's just a bunch of examples and case studies from their perspective.
I just want to ask, David, so when you speak about this bridge model, you make some rough analogy of these cars.
Right.
But do you try to make a link to real traffic models which people use, cell automata or whatever, where just everyday life experience, traffic jam or whatever comes?
Yeah, you can of course.
For the teachers, this would be very natural, right?
Right.
Especially in Israel. I mean.
Or it remains on this level, just formulated, say, macro process.
Of course, you can do that. The question is how much time you have in a course. Basically, that's the course we have is rather long. It's 14 weeks, 4 hours a week. And in addition, there is some tutorial and whatever. So it's a long course. And if you want to cover equilibrium, non-equilibrium, whatever, you know, it has to be, what you suggest is a very good thing for special topic course, you know. If you take, in addition to that basic course, you know, 2 hours a
I
week.
thought maybe for teachers it would be easier to link such a model issue substrate to, traffic.
Could be a good idea. Could be a good idea. Yeah. But my feeling is that I would have liked to do 2 things with teachers, you know, like reaching, you know, black body, and because they see that everywhere, you know. What is, you know, if you look at the light bulb, you know, what's the percentage of energy that you see, you know, all kind of practical things that you can, you know, estimate the temperature, you know, if you assume that also Earth is black body, you know, it's just reflecting, you can estimate the temperature. So you can do a lot of things. And the other thing is phase transitions, which is again something they see, they know, okay? Traffic models, again, that's of course, it's interesting and it's nice. It's I think, modeling, it's in modeling, that would be a good idea. But I think I would like to see the black body or whatever. I think it's of more importance when you need to talk to teachers.
Look, I think we hope to have more time for discussion, but now it's time for the coffee break. So otherwise they realize that we're not here, so the coffee break is going to be over. So let me join the coffee break.